Welcome to Deep Science Sleep. Settle yourself into the most comfortable position you can find. Let your body sink into the softness beneath you, releasing any tension you might be carrying in your shoulders, your neck, your jaw. Take a slow breath in through your nose, hold it gently for a moment, and then let it flow out through slightly parted lips. Feel the weight of your body pressing down, grounding you, anchoring you to this moment. Tonight, we're going to explore one of the most fascinating, mysterious, and counterintuitive realms of science, quantum physics. But don't worry, you don't need to concentrate hard or memorize anything. Just let the words wash over you like gentle waves, carrying you deeper into relaxation with each fact, each discovery, each strange and wonderful truth about the universe at its smallest scales. The quantum world doesn't follow the rules we're used to in our everyday experience. Down there, in the realm of atoms and photons, reality becomes fluid, uncertain, and beautifully bizarre. Tonight, let these quantum facts guide you into peaceful sleep as we journey through the foundations of modern physics. The quantum revolution, when reality became strange. At the turn of the 20th century, physics seemed nearly complete. Scientists believed they had figured out most of the fundamental rules governing the universe. Newton's laws explained how objects moved. Maxwell's equations described electricity and magnetism with mathematical precision. Thermodynamics explained heat and energy. The machinery of classical physics hummed along smoothly, a clockwork universe where everything had its place and followed predictable patterns. If you knew the initial conditions of any system precisely enough, you could calculate its future with perfect accuracy. The universe was deterministic, orderly, and fundamentally knowable. But then, something strange started happening. Experiments began producing results that simply didn't make sense according to classical physics. Light behaved in ways that couldn't be explained by waves alone. Atoms emitted energy in discrete chunks rather than continuous streams. And the more physicists looked at the microscopic world, the stranger it became. These weren't small discrepancies that could be explained away with better measurements or minor adjustments to existing theories. These were fundamental contradictions that would require a complete reimagining of how nature works at its most basic level. The revolution began, appropriately enough, with a crisis. In the late 19th century, physicists were trying to understand blackbody radiation. A blackbody is a theoretical perfect absorber and emitter of light. When heated, it glows, and the color of that glow depends on its temperature. Heat an iron poker in a fire, and it first becomes red, then orange, then white as it gets hotter. This progression of colors represents electromagnetic radiation being emitted at different wavelengths. Classical physics predicted that a blackbody should emit infinite amounts of energy at short wavelengths. This absurd result became known as the ultraviolet catastrophe. Obviously, this didn't happen in reality. Heated objects didn't emit infinite energy. There was clearly something wrong with the theory. Enter Max Planck, a German theoretical physicist working at the University of Berlin. On December 14, 1900, Planck presented a solution to the German Physical Society that would change physics forever, though he didn't realize it at the time. He proposed that energy could only be emitted or absorbed in discrete packets, which he called quanta. The energy of each quantum was proportional to its frequency, related by a fundamental constant that would later be named after him. Planck's constant, symbolized by the letter H. The value of this constant is incredibly small, about 6.626 times 10 to the negative 34 joule-seconds. This tiny number would become one of the most important values in all of physics. Planck's equation was deceptively simple. The energy of a quantum of radiation equals Planck's constant multiplied by the frequency of the radiation. This meant that higher frequency radiation, like ultraviolet light, came in larger energy chunks than lower frequency radiation like infrared. At low frequencies, many quanta could be emitted, but at very high frequencies, the energy per quantum became so large that it was statistically unlikely for a blackbody to have enough energy to emit them. This solved the ultraviolet catastrophe. The spectrum of blackbody radiation, which had been measured with great precision, fit Planck's formula perfectly. But here's the remarkable thing. Planck himself didn't really believe in the physical reality of his quanta. He thought they were just a mathematical trick, a convenient fiction that happened to give the right answer. In his own words, he called it an act of desperation. He had been struggling with this problem for years, trying to reconcile the experimental data with the established theories of physics. When he finally hit upon the idea of energy quantization, it violated everything he understood about how nature should work. Energy, according to classical physics, should be continuous. It should flow smoothly from one value to another, like water. The idea that it came in discrete chunks like grains of sand was deeply troubling to him. For several years after his groundbreaking paper, Planck tried to reintegrate his discovery back into classical physics. He attempted to eliminate the need for discrete quanta to find some way to explain his formula within the framework of continuous energy. He failed. Other physicists, including some of the most prominent names of the era, initially resisted the idea. Lord Rayleigh, James Jeans, and Hendrik Lorentz all tried to set Planck's constant to zero in their equations, attempting to recover the classical result. But the experiments kept showing that Planck was right. The constant had a definite non-zero value. Nature really did quantize energy at small scales. The true significance of Planck's work wouldn't become clear for another few years. In 1905, a patent clerk in Switzerland named Albert Einstein took Planck's idea seriously and applied it to a different problem: the photoelectric effect. When light shines on certain metals, it can knock electrons loose, creating an electric current. But experiments showed something odd. The energy of the ejected electrons didn't depend on the brightness of the light, as classical wave theory predicted. Instead, it depended on the color or frequency of the light. Dim blue light could eject electrons with high energy, while bright red light might not eject any electrons at all, no matter how intense. Einstein proposed that light itself comes in discrete quanta, which we now call photons. Each photon carries energy equal to Planck's constant times its frequency. When a photon strikes an electron in the metal, it transfers all its energy at once, like a billiard ball collision. If the photon's energy is high enough to overcome the binding energy holding the electron to the metal, the electron is ejected. Brighter light just means more photons, not more energetic photons. This explained the photoelectric effect perfectly, and it firmly established that light, despite also behaving like a wave, comes in particle-like packets of energy. For this work on the photoelectric effect, Einstein would receive the Nobel Prize in Physics in 1921. Ironically, he didn't win it for his theory of relativity, which he published in the same miraculous year of 1905. The Nobel Committee wanted to wait until relativity was more thoroughly tested. But the quantum theory of light, despite being equally revolutionary and even more counterintuitive, had overwhelming experimental support. Planck received his own Nobel Prize in 1918, nearly 2 decades after his original work, as the revolutionary nature of quantum theory gradually became clear to the physics community. By then, the quantum revolution was in full swing. Niels Bohr had applied quantum ideas to the structure of the atom, explaining how electrons could orbit the nucleus only at certain discrete energy levels, jumping between them by absorbing or emitting photons. Louis de Broglie proposed that if light could behave like a particle, then perhaps particles could behave like waves, an idea that would lead to the development of quantum mechanics proper. The world that emerged from these discoveries was fundamentally different from anything that had come before. The clockwork universe of Newton, where everything followed deterministic laws and precise trajectories, gave way to a probabilistic universe where particles didn't have definite properties until they were measured, where observation itself could change the outcome of experiments, and where the very act of trying to know something precisely could make something else uncertain. This was quantum mechanics, a theory that would prove to be the most accurate and successful description of nature ever devised, yet one that even its founders found philosophically troubling and conceptually bizarre. As you lie here in the darkness, consider this: the world as we experience it, solid and predictable, emerges from this quantum foundation that is neither solid nor predictable. Every atom in your body, every photon of light that entered your eyes today, every electron flowing through your nervous system follows these strange quantum rules. The universe doesn't just allow quantum behavior at small scales. It requires it. Without the quantum nature of electrons, atoms couldn't exist. Without the quantum nature of light, nuclear fusion couldn't power the sun. Without the peculiar rules of quantum mechanics, you and I and everything we see around us simply couldn't be. And so, as we continue our journey through quantum facts tonight, remember that we're not exploring some abstract mathematical fantasy. We're exploring the deep reality that underlies everything in existence. Let that thought ground you as your breathing deepens and your mind begins to drift towards sleep. The quantum world is strange, yes, but it is also the foundation upon which all the familiar aspects of reality are built. And there is something profoundly comforting in knowing that beneath the chaos and uncertainty of everyday life, there exist these fundamental truths, these elegant mathematical relationships that govern how the universe behaves, relationships that physicists have uncovered through patient observation, careful reasoning, and brilliant insight. Wave-particle duality, the double nature of reality. Imagine, if you will, that you're standing on a beach watching waves roll in from the ocean. Each wave rises and falls, spreads out as it approaches the shore, interferes with other waves, creating complex patterns of crests and troughs. Now imagine instead that you're watching a stream of tiny balls, each following its own trajectory, bouncing off obstacles, moving in straight lines between collisions. Waves and particles seem like fundamentally different types of things. Waves are spread out, diffuse, able to overlap and interfere with one another. Particles are localized, discrete, countable objects that occupy specific positions in space. In the classical world of everyday experience, something is either a wave or a particle. Cannot be both. Yet, in the quantum world, this distinction dissolves. Light, matter, everything at small enough scales exhibits both wave-like and particle-like properties, depending on how we choose to observe it. This dual nature was first demonstrated for light in a series of elegant experiments performed at the beginning of the 19th century, more than 100 years before quantum mechanics was formulated. The British polymath Thomas Young, working at the Royal Institution in London, conducted an experiment in 1801 that would become one of the most important in the history of physics. Young's experiment was beautifully simple. He allowed light from a single source to pass through two narrow parallel slits cut into an opaque barrier. On the far side of the barrier, he placed a screen to capture the pattern of light that made it through. If light consisted of particles, as Isaac Newton had proposed, Young expected to see two bright stripes on the screen, corresponding to the two slits. After all, particles passing through the left slit would hit the screen in one place, and particles passing through the right slit would hit another place. But that's not what Young saw. Instead, the screen showed multiple alternating bright and dark bands, a pattern of interference fringes. This is exactly what you would expect if light were a wave. As the light waves pass through the two slits, they spread out and overlap. Where two wave crests meet, they add together, creating a bright band. Where a crest meets a trough, they cancel out, creating darkness. The pattern on the screen is a map of constructive and destructive interference, unmistakable evidence that light propagates as a wave. Young's experiment seemed to settle the question decisively. Light is a wave, not a stream of particles as Newton had believed. For the next century, this wave picture of light dominated physics. Maxwell's equations, formulated in the 1860s, described light as electromagnetic waves, oscillations in electric and magnetic fields that could travel through empty space. The success of Maxwell's theory was stunning. It explained reflection, refraction, diffraction, interference, and even predicted the existence of radio waves, which were soon discovered. The wave nature of light appeared to be an established fact, confirmed by countless experiments and technological applications. But then came the 20th century and quantum theory. Einstein's explanation of the photoelectric effect required light to come in discrete particles, photons. This seemed to contradict the wave picture. How could light be both a wave that creates interference patterns and a stream of particles that kicks electrons out of metal? The paradox deepened as experimental techniques improved. By the mid-20th century, physicists could perform the double-slit experiment with light so dim that only one photon at a time passed through the apparatus. Each photon would arrive at the screen at a single point, a tiny flash registering at one specific location, exactly like a particle. But here's where it gets truly strange. When you perform this experiment sending one photon at a time and collect the results over many hours, gradually building up the pattern on the screen dot by dot, the interference pattern emerges. Even though each photon arrives as a localized particle, the collective pattern shows the wave-like interference. It's as if each photon somehow knows about both slits, even though it arrives at the screen at a single point. The photon seems to interfere with itself, taking both paths simultaneously as a wave, yet arriving as a localized particle. The strangeness doesn't end with light. In 1924, a French physicist named Louis de Broglie proposed something even more radical. If light, which everyone thought was a wave, could behave like a particle, perhaps particles like electrons, which everyone knew were particles, could behave like waves. He suggested that every particle has an associated wavelength, given by dividing Planck's constant by the particle's momentum. For large objects, this wavelength is vanishingly small, far too tiny to observe. But for electrons and other subatomic particles, the wavelength is comparable to atomic sizes, and wave effects should be observable. Within just a few years, de Broglie's hypothesis was confirmed. In 1927, Clinton Davison and Lester Germer at Bell Labs in the United States, and independently George Paget Thomson at the University of Aberdeen in Scotland, demonstrated that beams of electrons create diffraction patterns when scattered from crystal surfaces, exactly like X-rays or light waves do. Electrons, which everyone had thought of as tiny particles with definite positions, were producing interference effects that could only be explained if they propagated as waves. And then physicists did something remarkable. They performed the double-slit experiment with electrons. Just as with photons, when you send electrons one at a time through two slits, each one arrives at the detector at a single point, like a particle. But over time, the pattern that builds up shows interference fringes, like a wave. The electron, like the photon, seems to go through both slits simultaneously, interfering with itself, yet arriving at a definite location. This wave-particle duality has since been demonstrated for increasingly larger objects. In 1999, researchers in Vienna performed the double-slit experiment with buckyballs, molecules of 60 carbon atoms. In 2011, they extended it to even larger molecules containing more than 400 atoms. In 2019, experiments showed interference patterns for molecules with masses exceeding 2,000 atoms. All of these objects, from individual photons to complex molecules, exhibit the same fundamental dual nature. They propagate like waves, capable of interference and diffraction, yet interact like particles, transferring energy and momentum in discrete chunks at localized points. The wave-particle duality isn't a quirk of light or a peculiarity of electrons. It's a fundamental feature of quantum mechanics, applying to everything in the universe. Large objects don't show obvious wave behavior only because their quantum wavelengths are so small. A baseball thrown at 60 miles per hour has a de Broglie wavelength about 10 to the negative 34th meters, far smaller than the nucleus of an atom, impossible to detect. But the wavelength is there in principle. Perhaps the most unsettling aspect of wave-particle duality is what happens when you try to determine which slit a particle goes through. Scientists have devised clever experiments to detect, without disturbing the particle's trajectory, which path it takes. But every time you add a detector that gives you information about the particle's path, the interference pattern disappears. The screen shows two bright bands, just as you would expect for particles, not the multiple interference fringes characteristic of waves. The very act of determining which slit the particle went through destroys the wave-like behavior. This is not a limitation of experimental technique. It's not that we're disturbing the particle too much with our crude detectors. The effect persists even with the most gentle, sophisticated detection methods. It appears to be a fundamental feature of reality. When the particle's path is observable, even in principle, it behaves like a particle. When the path information is not available, it behaves like a wave. The particle's behavior depends on whether we could, in theory, determine which path it took, regardless of whether we actually look at that information. This observation led to long debates about the role of consciousness and observation in quantum mechanics. Does the universe somehow know whether we're watching? Do particles change their behavior based on whether a conscious observer will eventually see the results? Most physicists today don't think consciousness is relevant. Rather, the key distinction seems to be whether information about the particle's path becomes entangled with the environment in a way that could, in principle, be extracted. Once that happens, the quantum coherence necessary for wave-like interference is lost, a process called decoherence. We'll explore this more deeply later tonight. For now, as you settle further into relaxation, consider this remarkable fact. The electrons in your body, in the oxygen molecules you breathe, in the calcium atoms of your bones, all have both particle and wave nature. When they participate in chemical reactions, binding atoms together to form the molecules of life, they do so partly through their wave nature. The chemical bond itself is a quantum phenomenon, arising because electron waves can spread over multiple atoms, lowering the system's total energy. The solid feeling of the surface beneath you, the firmness of your own body, emerges from quantum wave functions determining how atoms arrange themselves and hold together. The philosophical implications of wave-particle duality continue to puzzle and fascinate physicists. The great quantum pioneer Niels Bohr introduced the concept of complementarity, arguing that wave and particle aspects are complementary descriptions that are both necessary for a complete understanding of quantum phenomena, yet mutually exclusive in any single observation. You can design an experiment to observe wave behavior or particle behavior, but not both simultaneously. The American physicist Richard Feynman, one of the architects of quantum field theory, often said that anyone who claims to understand quantum mechanics doesn't really understand quantum mechanics. He also frequently pointed out that all of quantum mechanics, all of its strangeness and counterintuitive features, can be understood by deeply contemplating the double-slit experiment. The lesson of wave-particle duality is that nature at its most fundamental level doesn't fit into the conceptual boxes we construct from everyday experience. Particles and waves are classical concepts, useful approximations that work well at large scales. But the quantum world is neither particles nor waves in the classical sense. It's something else entirely, something for which we don't have a simple mental picture because we didn't evolve to perceive or interact with individual atoms and photons. What we have instead are mathematical equations, the Schrödinger equation for matter waves, Maxwell's equations reinterpreted quantum mechanically for light, that describe with exquisite precision how these quantum entities behave. The equations work. They make predictions that have been tested countless times and confirmed to extraordinary precision. Yet translating the mathematics into intuitive pictures remains challenging. This is one of the profound insights of 20th century physics. Nature is not obligated to conform to our intuitions. The universe doesn't care whether we can visualize quantum mechanics or whether it makes common sense. It simply behaves the way it behaves, and we must adjust our thinking to match reality, not demand that reality adjust to match our preconceptions. There's something liberating about this, a reminder that the universe is far stranger and more interesting than we might imagine, full of surprises waiting to be discovered by careful observation and open-minded inquiry. As your breathing becomes slower and deeper, as your body releases the last tensions of the day, let the wave-particle duality remind you that reality has layers, depths that aren't immediately apparent. Just as a photon is simultaneously wave and particle, Reality itself contains aspects that seem contradictory from limited perspectives but form a coherent whole when viewed completely. Sleep now is approaching like a wave, building in amplitude, and like a particle it will arrive at a specific moment. Let both aspects carry you gently downward into rest. Quantum superposition, existing in multiple states. One of the most counterintuitive aspects of quantum mechanics is the principle of superposition. At its heart, superposition means that a quantum system can exist in multiple states simultaneously. Not that we don't know which state it's in, but that it is genuinely, physically in multiple states at the same time, at least until we make a measurement. This isn't just a statement about our knowledge or ignorance. It's a statement about the fundamental nature of reality at quantum scales. The quantum world allows for a kind of multiplicity, a being in several places at once that has no analog in our everyday experience. To understand superposition, we need to talk about quantum states. In quantum mechanics, the state of a system is described by a mathematical object called a wave function, typically denoted by the Greek letter psi. The wave function contains all the information that can be known about the system. For a particle, the wave function describes the probability of finding the particle at different locations with different momenta with different energies. The square of the wave function's amplitude at any point gives the probability of finding the particle there if you make a measurement. Here's the key insight. If a system can exist in state A, and it can exist in state B, then quantum mechanics allows it to exist in a superposition of both states simultaneously. The wave function is a mathematical combination of both states, weighted by complex numbers called probability amplitudes. The system isn't in state A or state B. It's in both states at once. When you finally make a measurement, the wave function collapses to one of the possible states, and you see a definite result. But before measurement, both possibilities coexist. The most famous illustration of superposition is Schrödinger's cat, a thought experiment proposed by Austrian physicist Erwin Schrödinger in 1935. Schrödinger was trying to highlight what he saw as the absurdity of quantum mechanics when applied to everyday objects. He imagined a cat sealed in a box with a diabolical device, a radioactive atom connected to a poison mechanism. If the atom decays, it triggers the release of poison, killing the cat. Quantum mechanics says that before we open the box and observe what happened, the atom is in a superposition of decayed and not decayed states. By extension, this means the cat should be in a superposition of alive and dead states, simultaneously breathing and not breathing, a macabre quantum zombie. Schrödinger intended this as a reductio ad absurdum, a demonstration that quantum mechanics must be incomplete or misunderstood because surely a cat can't be both alive and dead. But here's the thing. Quantum mechanics doesn't actually predict that macroscopic cats end up in superpositions. The cat is not an isolated quantum system. It's constantly interacting with the environment inside the box with air molecules, photons, thermal vibrations. These interactions cause rapid decoherence, collapsing any potential quantum superposition almost instantaneously into one classical state or the other. The cat is always definitely either alive or dead, never in a genuine superposition, because it's too large and too interactive with its environment to maintain quantum coherence. But for microscopic systems, superposition is very real. Consider an electron with a property called spin. Quantum spin is somewhat like the classical concept of rotation, but it's purely quantum with no real classical analog. An electron's spin can be measured along any direction, and the result will always be one of two values: spin up or spin down along that axis. If you measure an electron spin along the vertical direction and find it pointing up, then measure it again immediately, you'll find it still pointing up. The measurement has determined the electron's state. But now here's where superposition comes in. If you take that same electron and measure its spin along a horizontal direction instead, you'll find it has a 50% chance of being spin left and a 50% chance of being spin right. Before the measurement, the electron that was definitely spin up vertically was in a superposition of spin left and spin right horizontally. The states are related by a simple mathematical transformation. An electron that is definitely spin up along one axis is simultaneously in a superposition of both possible spin states along any perpendicular axis. This isn't about our ignorance of which state it's in. The electron genuinely exists in both states until we measure it. This has been verified countless times in laboratories around the world. Superposition isn't speculation or philosophy. It's measurable, reproducible, and forms the basis of modern technologies. Quantum computers, which we'll discuss later, rely entirely on superposition. A classical computer bit can be either 0 or 1. A quantum bit or qubit can be in a superposition of both 0 and 1 simultaneously. This allows quantum computers to perform certain calculations exponentially faster than classical computers, exploring many possible solutions in parallel through the magic of superposition. Experimental physicists have demonstrated superposition in increasingly dramatic ways. In laboratories around the world, researchers have created superposition states of ions, where a single charged atom is simultaneously in two places several micrometers apart, a distance enormous by atomic standards. They've created photons in superpositions of different paths through optical apparatus, traveling down two separate beam paths at the same time. They've even created superposition states of different numbers of photons in a cavity, the electromagnetic field simultaneously in a state of containing, say, 0 photons and 4 photons at the same time. One particularly striking demonstration involves superconducting circuits called SQUIDs, superconducting quantum interference devices. These are loops of superconducting material interrupted by insulating barriers. Electric current can flow around the loop in either direction, clockwise or counterclockwise. Physicists have created superposition states where a current of billions of electrons flows simultaneously in both directions at once. This brings quantum superposition from the scale of individual particles to something approaching the macroscopic, though still far smaller than Schrödinger's cat. The question of why we never see macroscopic superpositions, why Schrödinger's cat is always definitely alive or dead, is known as the measurement problem in quantum mechanics. When exactly does the quantum superposition collapse into a definite classical state? Is it when a measurement device interacts with the system? When a conscious observer looks at the result? When information about the system leaks into the environment? Different interpretations of quantum mechanics give different answers to these questions, and physicists still debate them today, nearly a century after the theory's inception. The Copenhagen interpretation, developed primarily by Niels Bohr and Werner Heisenberg in the 1920s, says that the wave function collapses upon measurement, but doesn't specify what exactly constitutes a measurement. The many worlds interpretation, proposed by Hugh Everett in 1957, says the wave function never collapses. Instead, when a measurement occurs, the universe splits into multiple branches, one for each possible outcome, and all outcomes actually happen in different parallel universes. The decoherence interpretation, which has gained favor in recent decades, explains wave function collapse as an apparent effect arising from the quantum system becoming entangled with its environment in complex ways that destroy coherent superpositions. Regardless of interpretation, the mathematics of superposition is clear and unambiguous. The Schrödinger equation, the fundamental equation of quantum mechanics, is linear. This mathematical property means that if state A is a solution and state B is a solution, then any combination of A and B is also a solution. Superposition is built into the mathematical structure of the theory at the most fundamental level. It's not an add-on or a peculiar consequence. It's a basic axiom, part of the foundation upon which the entire edifice of quantum mechanics is constructed. The principle of superposition has profound implications for our understanding of reality. It suggests that the classical world of definite properties and unique states is an approximation, a kind of averaged-out, emergent description of an underlying quantum reality that is far richer and stranger. At the quantum level, particles don't have single, well-defined properties. They exist in clouds of potentiality, simultaneously possessing multiple values for observable quantities, actualizing into definite values only when forced to do so by measurement or interaction. There's a certain poetry to this, a suggestion that reality at its deepest level is more fluid and less determinate than our everyday experience suggests. The universe maintains possibilities, holds open options, exists in states of becoming rather than simply being. Only when the quantum system interacts strongly enough with the classical world do these possibilities crystallize into actuality. And even then, the other possibilities don't simply vanish. In some interpretations, they continue to exist in other branches of the wave function or in the correlations between system and environment. As you lie here in the darkness, your own body is composed of countless quantum systems in various states of superposition. Electrons in the molecules of your cells exist in superposition states that make chemical bonding possible. Photons absorbed by your retina during the day entered your eye in superpositions of different polarization states. The protons in your DNA, the atoms in your neurotransmitters, all obey the laws of quantum mechanics, including superposition. Yet somehow, from this quantum substrate, emerges your conscious experience, your sense of existing as a single definite entity in a single definite state. The relationship between quantum superposition and classical definiteness, between the microscopic world of possibilities and the macroscopic world of actualities, remains one of the deepest mysteries in physics. How do we get from there to here? How does the quantum become classical? How do superpositions resolve into single outcomes? These questions probe the boundary between physics and philosophy, between what we can measure and what we can understand. Let the concept of superposition invite you to consider the multiplicity within unity, the way that from one perspective, many things can be true simultaneously, even if from another perspective only one manifests. In dreams, you'll soon experience your own kind of superposition, where normal rules don't apply, where you can be in many places, many situations, holding contradictory possibilities together in the fluid logic of the sleeping mind. Quantum mechanics teaches us that at the deepest level, reality itself has this dreamlike quality, this openness to multiple simultaneous truths, resolving into classical definiteness only when required by the demands of observation and interaction. Rest now in that quantum uncertainty, that space of possibility, as sleep draws you down into its embrace. Quantum entanglement, spooky action at a distance. Let's begin our journey in the early 1930s, in a world where physics was in turmoil. For centuries, scientists had believed they understood how the universe worked. Newton's laws governed the motion of planets and falling apples alike. Everything was predictable, deterministic, knowable. But then came quantum mechanics, and with it, a revelation so disturbing that it would haunt Albert Einstein for the rest of his life. Picture Einstein in 1935, sitting in his office at the Institute for Advanced Study in Princeton, New Jersey. He had fled Nazi Germany just 2 years earlier, seeking refuge in America. But even in this new land, he could find no peace from the quantum demons that plagued his thoughts. Along with 2 colleagues, Boris Podolsky and Nathan Rosen, Einstein was crafting what he hoped would be the definitive argument against quantum mechanics as it was then understood. Their paper, published that year, would become known as the EPR paradox, named for the initials of its 3 authors. The EPR thought experiment was elegant in its simplicity, yet devastating in its implications. Imagine Einstein proposed that you create 2 particles that interact in a specific way, becoming what we now call entangled. According to quantum mechanics, before you measure either particle, neither one has definite properties. They exist in what's called a superposition, a kind of quantum limbo where they simultaneously possess multiple possible values. The wave function, that mathematical description of quantum states, contains all the information we can know about the system, but it doesn't tell us what any specific measurement will reveal until we actually perform that measurement. Here's where things get strange. Once these particles are entangled, they remain connected no matter how far apart they travel. Measure one particle and you instantly know something about the other, even if it's on the opposite side of the galaxy. If you measure the spin of one entangled electron and find it pointing up, you'll know with absolute certainty that measuring its partner will reveal spin pointing down. The correlation is perfect, instantaneous, and, from Einstein's perspective, deeply troubling. Einstein called this spooky action at a distance, and he meant it as a criticism. His theory of special relativity, published 30 years earlier, had established that nothing could travel faster than light. Information itself was bound by this cosmic speed limit. Yet quantum entanglement seemed to suggest that information could be transmitted instantaneously across any distance. How could this be reconciled with relativity? Einstein, Podolsky, and Rosen argued that quantum mechanics must be incomplete. There must be, they insisted, hidden variables, additional properties that particles possess but that quantum theory doesn't account for. Each particle must carry with it, from the moment of its creation, predetermined values for all its properties. When we measure one particle and seem to affect its distant partner, we're not actually transmitting information faster than light. We're simply revealing information that was already present in both particles all along. To understand their argument, consider an analogy. Imagine you have a pair of gloves, one left-handed and one right-handed. You put each glove in a separate box without looking, then ship one box to Tokyo and keep the other in New York. When you open your box in New York and discover a left-handed glove, you instantly know that the box in Tokyo contains a right-handed glove. Nothing mysterious here, The information was determined when you packed the boxes, not when you opened them. Einstein believed quantum entanglement was like the gloves. The properties were determined at the source, not at the moment of measurement. Quantum mechanics, he argued, was simply missing this deeper layer of reality, the hidden variables that predetermined everything. For decades, the EPR paradox remained a purely philosophical debate. Sure, Einstein's reasoning seemed sound, but how could you test it experimentally? The turning point came in 1964, when Irish physicist John Stuart Bell published a paper that would fundamentally change our understanding of reality. Bell's theorem was a marvel of logical reasoning. He showed that any theory based on local hidden variables, Einstein's preferred explanation, must obey certain mathematical constraints called Bell's inequalities. The beauty of Bell's theorem was that it made testable predictions. Quantum mechanics predicted correlations between entangled particles that would violate Bell's inequalities, while local hidden variable theories predicted correlations that would obey them. For the first time, this abstract philosophical debate could be settled in the laboratory. The first attempts to test Bell's theorem came in the early 1970s. In 1972, Stuart Friedman and John Clauser at the University of California, Berkeley, performed the first experiment designed specifically to test Bell's inequalities using polarized photons from calcium atoms. Their results supported quantum mechanics, showing violations of Bell's inequalities. But the experiment had limitations. The measurements weren't sufficiently separated in space and time to definitively rule out faster-than-light communication between the detectors. This is where Alain Aspect enters our story. A French physicist working at the Institut d'Optique in Orsay, Aspect spent years in the late 1970s and early 80s designing and conducting increasingly sophisticated experiments to test Bell's theorem. His goal was to close the loopholes in earlier experiments and provide definitive answer. Aspect's breakthrough came in 1982. He and his colleagues, Gerard Roger, Philippe Grangier, and Jean Dalibard, created pairs of entangled photons using laser-excited calcium atoms. But here was the innovation. They used fast-switching devices to change the measurement settings while the photons were already in flight, traveling to the detectors. The switches operated so quickly that if any signal were traveling from one detector to the other at the speed of light, it wouldn't have time to arrive before the measurement was complete. The results were unambiguous. Quantum mechanics was right. Bell's inequalities were violated. The statistical correlations between the entangled photons were stronger than any local hidden variable theory could explain. Einstein's intuition, it seemed, was wrong. Reality is not locally realistic in the way he had hoped. Think about what this means. It's not just that quantum mechanics is weird, we already knew that. It's that the universe itself operates in a way that defies our deepest intuitions about how things should work. The properties of entangled particles are not predetermined. They are genuinely uncertain until measured, and yet they remain correlated in a way that transcends space. Now, before we get too carried away, let's be clear about what entanglement does not allow. Despite what you might read in science fiction, you cannot use entanglement to send messages faster than light. When you measure an entangled particle, you get a random result. Your measurement does instantaneously affect the state of the distant particle, but from the perspective of someone measuring that distant particle, their result also appears random. Only when you bring the measurement results together and compare them do you see the correlations. Information still respects Einstein's speed limit. In the decades since aspects experiments, the technology for creating and manipulating entangled particles has advanced dramatically. In 1997, Anton Zeelinger's group in Austria achieved quantum teleportation, using entanglement to transfer the quantum state of one particle to another distant particle. In 2012, researchers created entanglement between particles separated by 143 kilometers. By 2017, Chinese scientists had demonstrated satellite-based quantum entanglement across distances of more than 1,200 kilometers. These aren't just impressive laboratory demonstrations. Entanglement has become the foundation for emerging quantum technologies. Quantum cryptography uses entangled particles to create perfectly secure communication channels. Any attempt to eavesdrop would disturb the entanglement and reveal the presence of the intruder. Quantum computers harness entanglement to perform certain calculations exponentially faster than classical computers ever could. In 2022, the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their groundbreaking experiments with entangled photons. The Nobel Committee's citation explicitly noted that their work had established violations of Bell's inequalities and pioneered quantum information science. The philosophical implications of entanglement are still being debated. Some physicists embrace the non-local nature of quantum mechanics, accepting that the universe has connections that transcend space and time. Others, following interpretations like the many worlds interpretation, argue that entanglement doesn't involve action at a distance at all. Instead, measurements cause the universe to split into multiple branches with different outcomes in each branch. What's certain is that entanglement has forced us to abandon some deeply held beliefs about reality. The universe is not a collection of separate objects, each with its own independent properties. At the quantum level, objects that have interacted remain fundamentally connected, their fates intertwined in ways that violate our classical intuitions. Einstein's spooky action at a distance is real. It's been experimentally verified thousands of times, and it's now a cornerstone of cutting-edge technology. As we drift deeper into this quantum realm, let that strangeness wash over you. The universe is more interconnected, more mysterious, and more wonderful than the everyday world suggests. The uncertainty principle, limits of what we can know. Now let's journey to 1927, to a different kind of quantum revolution. While Einstein was troubled by entanglement's implications for the completeness of quantum theory, a young German physicist named Werner Heisenberg was grappling with even more fundamental questions about what we can know about the quantum world. Heisenberg was just 25 years old, but already recognized as a brilliant theorist. He was working with Niels Bohr in Copenhagen, trying to understand the strange behavior of atoms and electrons. The quantum theory that was emerging seemed to work mathematically. It could predict the outcomes of experiments with remarkable accuracy. But what did it all mean? What was really happening inside an atom? One evening in February 1927, while Bohr was away on a skiing vacation in Norway, Heisenberg had a breakthrough. He was thinking about the limits of measurement at the atomic scale, and he realized something profound. There's a fundamental limit to how precisely we can simultaneously know certain pairs of properties of quantum particles. The most famous version of this principle concerns position and momentum, where a particle is and how fast it's moving. Heisenberg showed that the more precisely you measure a particle's position, the less precisely you can know its momentum, and vice versa. This isn't because of limitations in our measuring instruments. It's not that better technology would let us measure both properties precisely. The limitation is fundamental, woven into the fabric of quantum reality itself. To understand why, imagine trying to measure the position of an electron. You need to see it somehow, which means bouncing light off it. But light comes in packets called photons, and photons carry momentum. When a photon hits the electron to reveal its position, it transfers momentum to the electron, changing the very property, the electron's momentum, that you might want to measure next. The more precisely you want to know the position, which requires using light with shorter wavelengths and thus higher energy, the more you disturb the momentum. But here's the deeper truth that Heisenberg uncovered. This isn't just about the disturbance caused by measurement. The uncertainty is more fundamental than that. Before any measurement, the particle simply doesn't have definite values for both position and momentum simultaneously. It's not that we don't know these values. It's that the values don't exist in any meaningful sense. Heisenberg captured this in a mathematical relationship, though the exact form we use today was refined by Earl Kennard later that same year. The uncertainty principle states that the product of the uncertainties in position and momentum must be greater than or equal to a tiny number. Planck's constant divided by 4 times pi. In mathematical form, it's written as delta x times delta p is greater than or equal to h bar over 2, where h bar is Planck's constant divided by 2 times pi. Planck's constant is incredibly small, about 6.6 times 10 to the negative 34th joule seconds. This is why we don't notice quantum uncertainty in everyday life. For large objects like baseballs or cars or people, the uncertainty is so tiny compared to the object's size and momentum that it's utterly negligible. You can know both where your car is and how fast it's moving with perfect adequacy for any practical purpose. But for something as small as an electron, the uncertainty principle is significant. An electron in an atom is confined to a region about 1/10 of a nanometer across. Given this constraint on its position, the uncertainty principle tells us that the electron must have a significant uncertainty in its momentum, which translates to a significant uncertainty in its energy. This zero-point energy, the minimum energy a quantum system can have, exists even at absolute zero temperature, where classically everything should be completely still. The uncertainty principle isn't limited to position and momentum. It applies to any pair of what physicists call conjugate variables, properties that are related in a specific mathematical way. Another important example is energy and time. The more precisely you measure the energy of a quantum system, the longer it takes to make that measurement. Conversely, if you want to measure energy quickly, you'll get a less precise result. This energy-time uncertainty has profound implications. It means that for very brief moments, a quantum system can borrow energy from empty space, violating conservation of energy, as long as it pays that energy back quickly enough. The shorter the time interval, the larger the energy fluctuation that's allowed. This is the origin of virtual particles, which we'll encounter again when we discuss the quantum vacuum. Heisenberg's uncertainty principle shook the foundations of physics. For centuries, physics had been based on the idea that the world is, in principle, perfectly knowable. If you know the exact position and momentum of every particle in the universe at one moment, classical physics says you can predict the exact state of the universe at any future moment. This is called determinism, and it was central to the scientific worldview. The uncertainty principle destroyed this hope. Not only can you not know both position and momentum exactly, but even if you could, quantum mechanics tells us that the future behavior of the system would still be probabilistic, not deterministic. The universe, at its most fundamental level, is inherently uncertain. Einstein, predictably, was deeply troubled by this. He famously quipped that God does not play dice with the universe. He believed that beneath the probabilistic predictions of quantum mechanics must lie a deeper, deterministic reality, those hidden variables again. But experiments, particularly those testing Bell's theorem, have consistently shown that Einstein was wrong. The uncertainty isn't just epistemic about our knowledge, it's ontological about the nature of reality itself. Think about the philosophical implications. We're used to thinking of ourselves as observers of an objective reality that exists independent of our observations. But the uncertainty principle suggests a different picture. At the quantum level, there is no sharp distinction between observer and observed. The act of measurement doesn't just reveal properties. It participates in creating them. Before you measure an electron's position, it doesn't have a precise position. It exists as a cloud of probability spread throughout space. Your measurement collapses that cloud into a definite location, but only by introducing uncertainty into the momentum. The uncertainty principle also helps explain why atoms are stable. In classical physics, if electrons orbited the nucleus like tiny planets, they would constantly radiate energy and spiral into the nucleus in a fraction of a second. But the uncertainty principle prevents this. If an electron were to spiral into the nucleus, its position would become very precisely defined right at the nucleus, which would require its momentum to become enormously uncertain. This would give the electron a huge kinetic energy, pushing it back out. The result is that electrons settle into stable orbits, or more accurately, stable probability clouds around the nucleus. The principle has practical implications too. The precision of our best atomic clocks is ultimately limited by the uncertainty principle. In GPS satellites, time measurements need to be incredibly precise. Errors of nanoseconds translate to positioning errors of feet. Engineers have to account for both relativistic effects and quantum uncertainties when designing these systems. In quantum computers, the uncertainty principle is both a challenge and an opportunity. The inherent quantum fuzziness makes it hard to maintain the delicate quantum states needed for computation. This is part of the decoherence problem we'll discuss later. But that same fuzziness is what gives quantum computers their power, allowing them to explore multiple solutions simultaneously. Heisenberg himself came to see the uncertainty principle as revealing something profound about nature. In his book, The Physical Principles of the Quantum Theory, he wrote, "Any use of the words position and velocity, with accuracy exceeding that given by the uncertainty relation, is just as meaningless as the use of words whose sense is not defined." Modern physics has deepened our understanding of the uncertainty principle. We now know it's not unique to quantum mechanics. Any theory with wave-like properties will have similar limitations. But the quantum version is special because it applies to everything in nature. Electrons, atoms, molecules, even large molecules like buckyballs, 60 carbon atom spheres, have been shown to exhibit wave-like behavior and obey the uncertainty principle. As we lie here contemplating this, consider. The uncertainty at the heart of quantum mechanics isn't a bug in our understanding. It's a feature of reality. The universe is fundamentally probabilistic, fundamentally uncertain, and that's not a limitation. It's what makes the rich complexity of our world possible. Without quantum uncertainty, matter wouldn't have the properties it does. Chemistry wouldn't work the way it does. And we, complex, conscious beings made of quantum particles, wouldn't exist to ponder these mysteries. Quantum tunneling, passing through impossible barriers. Let's shift our attention to another quantum phenomenon that seems to defy common sense. Quantum tunneling. This effect is so strange that when it was first proposed, many physicists simply couldn't believe it was real. Yet today we know it's not only real, it's essential to the existence of stars, to the operation of modern electronics, and quite possibly to life itself. Imagine you're rolling a ball toward a hill. In the classical world we experience every day, the outcome is predictable. If the ball doesn't have enough energy to reach the top of the hill, it rolls back down. It can't somehow magically appear on the other side of the hill without first going over the top. The hill is a barrier, and you need sufficient energy to overcome it. Now imagine that ball is an electron, and the hill is an energy barrier, perhaps the electrical repulsion between two atomic nuclei, or the potential energy that keeps an electron bound to an atom. Quantum mechanics makes a bizarre prediction. Even if the electron doesn't have enough energy to overcome the barrier, there's a probability, sometimes a substantial one, that it will appear on the other side anyway. It tunnels through the barrier, taking a shortcut that classical physics says is absolutely forbidden. The explanation lies in the wave nature of quantum particles. Remember that every particle can be described by a wave function, which represents the probability of finding the particle at different locations. When a quantum wave encounters a barrier, something interesting happens. Even though most of the wave reflects back, a small part of it extends into the barrier region and emerges on the other side. Here's the crucial point. Wherever the wave function has non-zero amplitude, there's a probability of finding the particle. So even though classically the particle shouldn't be able to penetrate the barrier, quantum mechanically there's a small but real probability that it will leak through to the other side. This isn't because the particle digs through or finds a gap. It's a purely quantum phenomenon with no classical analog. The probability of tunneling depends on several factors: the height and width of the barrier, and the mass and energy of the particle. The higher and wider the barrier, the less likely tunneling becomes. And because tunneling probability decreases exponentially with particle mass, we only observe it for very small particles like electrons, protons, and small atoms. You'll never see a person or a cat or even a single cell tunnel through a wall. The probability is so incredibly small that it would never happen even in the lifetime of the universe. But for subatomic particles, tunneling happens all the time. In fact, it's happening inside the sun right now, and has been for billions of years. This is perhaps the most dramatic and important example of quantum tunneling in nature. The sun shines because of nuclear fusion in its core. Specifically, hydrogen nuclei, protons, fuse together to form helium, releasing enormous amounts of energy in the process. But here's the problem. Protons are positively charged, and like charges repel each other. To fuse, two protons need to get incredibly close together, close enough for the strong nuclear force to overcome their electrical repulsion and bind them. Classical physics says this should require temperatures of about 100 million Kelvin. The sun's core is hot, about 15 million Kelvin, but that's nowhere near hot enough. At 15 million Kelvin, the protons simply don't collide with enough energy to overcome their mutual repulsion. If classical physics were correct, the sun shouldn't be able to sustain nuclear fusion. It shouldn't shine. Enter George Gamow, a brilliant Russian-American physicist. In 1928, Gamow applied the newly developed quantum mechanics to the problem of nuclear fusion and radioactive decay. He showed that particles don't need enough energy to classically overcome the barrier. They can quantum tunnel through it. For fusion in the sun, this means that protons with energies far below what's classically required can still have a small but real probability of getting close enough to fuse. Now, the tunneling probability for any individual collision is extraordinarily small, roughly 1 in 10 to the 28th power. But the sun's core contains an unimaginable number of protons, and they're colliding constantly. With about 10 to the 56 protons in the sun and countless collisions every second, even that tiny tunneling probability leads to enough fusion reactions to power the sun for billions of years. Think about this for a moment. The sun wouldn't shine without quantum tunneling. Earth wouldn't receive the light and heat necessary for life. The entire basis for life in our solar system depends on this supposedly impossible quantum phenomenon. We exist because quantum mechanics allows the sun to burn at temperatures far below what classical physics would require. Quantum tunneling is also crucial for radioactive decay, another phenomenon that Gamow explained. In alpha decay, an alpha particle, 2 protons and 2 neutrons bound together, escapes from an atomic nucleus. Classically, the alpha particle is trapped inside the nucleus by a strong potential barrier. The particle doesn't have enough energy to climb over this barrier. Yet radioactive decay happens, the alpha particle somehow gets out. Again, quantum tunneling provides the answer. The alpha particle's wave function extends slightly beyond the nucleus, into and through the barrier. There's a small probability that the particle will be found outside the nucleus, and when this happens, it's free. The tunneling probability depends on the barrier's height and width, which is why different radioactive isotopes have vastly different half-lives. Some decay in fractions of a second, others take billions of years. The Scanning Tunneling Microscope, or STM, is a technological marvel that harnesses quantum tunneling to image individual atoms. Invented in 1981 by Gerd Binnig and Heinrich Rohrer at IBM's research laboratory in Zurich, they won the Nobel Prize in 1986 for this work. The STM uses an incredibly sharp metal tip, so sharp that it ends in just a single atom. When this tip is brought within a nanometer or so of a conducting surface, electrons can tunnel between the tip and the surface. The tunneling current depends extremely sensitively on the distance, exponentially so, in fact. As the tip scans across the surface, the current rises and falls as it encounters atoms. By monitoring these tiny changes in current, scientists can create images showing the arrangement of individual atoms on a surface. The STM opened up the world of nanotechnology, allowing us not just to see individual atoms but to manipulate them. But perhaps the most intriguing possibility is that quantum tunneling plays a role in biology. This is still a frontier of research, but evidence is mounting that life exploits quantum effects, including tunneling, in surprising ways. Consider DNA mutations. The structure of DNA, the famous double helix, is held together by hydrogen bonds between base pairs. These bonds form when hydrogen atoms sit at specific positions, allowing them to bridge between the two DNA strands. But quantum tunneling might allow these hydrogen atoms to occasionally shift from their normal positions to different, unusual positions. If this happens during DNA replication, it could cause a mutation, a change in the genetic code. This idea, first proposed in the 1960s by Perloff-Lovedan, suggests that some spontaneous mutations might have a quantum origin. The hydrogen atom tunnels from one position to another, changing which base pairs can form. While this is still controversial, experiments have shown that hydrogen transfer in DNA base pairs can indeed involve tunneling, and that the tunneling rate is affected by factors like temperature and the surrounding chemical environment. Quantum tunneling might also be important in enzyme catalysis, the way biological catalysts speed up chemical reactions. Some reactions in living cells involve the transfer of hydrogen atoms, or more precisely, protons or hydrogen atoms' electrons, from one molecule to another. Classical chemistry says these transfers should be slow at body temperature. But if tunneling is involved, the transfers can happen much faster, potentially explaining how enzymes achieve such remarkable catalytic power. Smell might even involve quantum tunneling. The traditional theory of olfaction says we smell molecules based on their shape. Different shapes fit into different receptor proteins in our noses like keys into locks. But an alternative quantum theory, championed by biophysicist Luca Turin, proposes that smell works more like a highly sensitive spectroscope. According to this theory, when an odor molecule binds to a receptor, an electron can tunnel from one side of the receptor to the other, but only if the odor molecule vibrates at just the right frequency. Different molecules have different vibrational frequencies, allowing us to distinguish them by smell. This is still hotly debated, and the shape theory probably explains most of how smell works. But there's some experimental evidence that supports a quantum component to olfaction. For instance, molecules with the same shape but different isotopic composition, and thus different vibrational frequencies, can sometimes smell different to sensitive noses. In modern technology, quantum tunneling is everywhere. The flash memory in your smartphone, tablet, or USB drive works by trapping electrons in tiny isolated regions called floating gates. These electrons tunnel in and out through thin insulating barriers. You're literally writing and erasing data via quantum tunneling billions of times whenever you use your device. Some of the latest transistors in computer chips are so small that electrons can tunnel through regions they're supposed to be confined in, creating unwanted leakage currents that waste power and generate heat. Engineers designing next-generation computer chips have to account for quantum tunneling effects that would have been negligible in larger, older transistors. The philosophical implications of tunneling are worth pondering. In classical physics, barriers are absolute. You either have enough energy to overcome them or you don't. But quantum mechanics introduces genuine possibility where classical physics sees only impossibility. A particle facing a barrier exists in a superposition of states, transmitted and reflected. Only when measured does it decide which outcome occurred. This might seem like merely a curiosity about tiny particles, but tunneling reminds us that the boundaries we perceive in the world aren't as rigid as they appear. The impossible becomes merely improbable, and given enough time and enough opportunities, even the improbable becomes inevitable. As you relax into sleep, imagine the quantum tunneling happening all around and within you. Inside every cell, enzymes are facilitating reactions that might involve quantum tunneling. The sun continues to shine above us, sustained by protons tunneling through energy barriers. Your electronic devices store information via electrons tunneling through impossibly thin barriers. The quantum realm doesn't just exist in physics laboratories. It's woven into the fabric of existence, making possible a universe far richer and stranger than classical physics ever suggested. The quantum vacuum, empty space that isn't empty. Now we turn to perhaps the most philosophically provocative aspect of quantum mechanics: the quantum vacuum. The very phrase seems like a contradiction. A vacuum, by definition, is empty space. Remove all the particles, remove all the energy, cool everything to absolute zero, and you should have nothing, right? Wrong. Quantum mechanics tells us that even in the purest vacuum, completely devoid of any real particles, space itself seethes with activity. The vacuum is not empty. It's filled with quantum fluctuations, with virtual particles constantly appearing and disappearing, with a background of zero-point energy that can never be eliminated. This isn't speculation or science fiction. It's been experimentally verified in multiple ways, and it has profound implications for our understanding of reality. The key to understanding the quantum vacuum lies in Heisenberg's uncertainty principle, which we discussed earlier. Remember that the uncertainty principle applies not just to position and momentum, but to energy and time as well. The more precisely you know the energy of a system, the less precisely you can pin down when that energy is present. Flip this around. If you look at a system for a very brief interval of time, the energy becomes highly uncertain. Even in empty space, we can apply the uncertainty principle. If we examine a tiny region of space for a very brief moment, the energy in that region is fundamentally uncertain. This uncertainty in energy means that, for fleeting instants, particle-antiparticle pairs can appear out of nothing, borrow energy from the vacuum, exist for a time determined by the uncertainty principle, and then annihilate back into nothingness. These are called virtual particles, and they're one of the strangest predictions of quantum field theory. A virtual electron-positron pair, for example, can spontaneously appear in empty space, exist for about 10 to the negative 21 seconds, and then annihilate. The more energy the particles have, the shorter time they can exist. The vacuum becomes a bubbling quantum foam of virtual particles of all types, electrons and positrons, quarks and antiquarks, even virtual photons. Now, you might wonder, if these particles appear and disappear so quickly, and if they can't be directly observed, how do we know they're real? The answer is that while virtual particles themselves can't be captured and measured, they have real, observable effects. They're not just mathematical conveniences or artifacts of our calculations. They have genuine physical consequences. The most famous of these is the Casimir effect, predicted in 1948 by Dutch physicist Hendrik Casimir. Casimir was thinking about the quantum vacuum and had a remarkable insight. Imagine you take two uncharged metal plates and place them very close together in a vacuum, separated by just a few nanometers. According to quantum field theory, the virtual particles between the plates are restricted. Only certain wavelengths can fit in that tiny gap. But outside the plates, in the open vacuum, all wavelengths of virtual particles are possible. This creates an imbalance. There are, in a sense, more virtual particles outside the plates than between them. This difference in the density of quantum fluctuations creates a tiny but measurable force pushing the plates together. Casimir calculated this force and predicted that it should be detectable for plates separated by distances of a few micrometers or less. For decades, the Casimir effect remained a theoretical curiosity. The forces involved are incredibly small. For 1 square centimeter plates separated by 1 micrometer, the attractive force is only about the weight of a few nanograms. But in 1948, when Casimir made his prediction, the experimental techniques needed to measure such tiny forces simply didn't exist. That changed in 1996 when physicist Steve Lamorot, then at the University of Washington, performed the first precision measurement of the Casimir force. Using a torsion pendulum, a device that can detect extremely small forces by measuring tiny twists, Lamorot confirmed that the force between a plate and a sphere matched Casimir's predictions to within 5% accuracy. Since then, the Casimir effect has been measured many times with increasing precision. Modern experiments confirm the theoretical predictions to better than 1% accuracy. There's no doubt the quantum vacuum has real, measurable effects. Empty space isn't empty. The Casimir effect has practical implications. In nanomachines and microelectromechanical systems, where components are separated by distances of nanometers, Casimir forces can cause parts to stick together unexpectedly. Engineers designing these tiny devices have to account for quantum vacuum effects that would be utterly negligible at larger scales. Interestingly, the Casimir force isn't always attractive. In 2009, scientists demonstrated a repulsive Casimir effect for the first time. By immersing materials with specific properties in a fluid, they created a situation where the quantum fluctuations actually pushed objects apart rather than pulling them together. This opens up fascinating possibilities for frictionless nanomachines, since objects could be suspended by quantum vacuum forces without touching. Another manifestation of quantum vacuum effects is the Lamb shift, discovered by Willis Lamb in 1947. Lamb was studying the spectrum of hydrogen, the specific frequencies of light that hydrogen atoms absorb and emit. According to Paul Dirac's theory of the electron, certain energy levels in hydrogen should have exactly the same energy. But Lamb found a tiny split between them, with one level slightly higher than predicted. This Lamb shift arises because the electron in the hydrogen atom is constantly interacting with virtual photons in the quantum vacuum. These virtual photons cause the electron to jitter slightly in its position, and this jittering changes the energy levels in a measurable way. The agreement between theoretical calculations of the Lamb shift and experimental measurements is one of the most precise confirmations of quantum electrodynamics, accurate to better than 1 part in a million. The quantum vacuum also plays a crucial role in understanding how particles acquire mass. The Higgs field, whose discovery in 2012 earned the Nobel Prize, is a quantum field that permeates all of space. It's part of what we call the vacuum. Elementary particles acquire mass by interacting with this Higgs field. The stronger the interaction, the more massive the particle. But perhaps the most profound and problematic connection between the quantum vacuum and the nature of reality involves cosmology and the structure of the universe itself. If the quantum vacuum has energy, as the Casimir effect demonstrates, then empty space itself has energy. And according to Einstein's general theory of relativity, energy and mass are equivalent, and both curve spacetime. This means the quantum vacuum should gravitate. It should contribute to the cosmological constant, a term in Einstein's equations that describes the energy density of empty space. Einstein originally introduced this constant in 1917 for a different reason. He wanted his equations to allow for a static universe, and he needed the cosmological constant to counterbalance gravity. #quantum decoherence and modern quantum technologies. #documentary script for deep science sleep. How quantum becomes classical. Let's start with what makes quantum mechanics so peculiar in the first place. In the quantum world, particles exist not as definite things with precise properties, but as clouds of possibility described by what physicists call a wave function. An electron doesn't simply spin in one direction or another until we measure it. Instead, it exists in a superposition, simultaneously spinning in multiple directions at once, each possibility represented with a certain probability amplitude. These probability amplitudes are complex numbers, meaning they have both a magnitude and a phase. Think of the phase like the position of a hand on a clock face. When quantum systems interact or combine, these phases matter enormously. Two quantum possibilities can interfere with each other constructively, like waves building on each other, or destructively, like waves canceling each other out. This interference is the hallmark of quantum behavior. It's what creates the famous double-slit experiment pattern, where individual particles somehow know about both paths through a barrier and create an interference pattern on a detector screen. Now here's where decoherence enters the story. Quantum systems don't exist in perfect isolation. They're constantly bumping into their environment, photons of light, molecules of air, vibrations in whatever substrate they're sitting on. Each of these interactions is itself a quantum process, and here's the crucial insight that emerged in the 1970s and 80s. When a quantum system interacts with its environment, the two become entangled. Imagine you have a quantum particle in a superposition of being in two different locations at once. Call these possibilities A and B. When a photon from the environment bounces off this particle, the photon itself becomes entangled with the particle state. If the particle is at location A, the photon scatters in one particular way. If the particle is at location B, the photon scatters differently. Now the combined system, particle plus photon, has become correlated. The quantum information that was once localized in the particle has spread out into the environment. But the environment isn't just one photon. It's vast, an essentially infinite collection of particles, each with many degrees of freedom. As our quantum particle interacts with more and more environmental particles, the entanglement spreads like ink diffusing through water. The particle's quantum state becomes correlated with thousands, millions, billions of environmental degrees of freedom. Each environmental particle carries away a tiny bit of information about which state the particle is in. Here's the remarkable consequence. From the perspective of someone observing just the particle itself, ignoring all those environmental particles, the interference between the different quantum possibilities effectively vanishes. The different components of the superposition, state A and state B, can no longer interfere with each other because their phase relationship has become scrambled through entanglement with the environment. To restore interference, you would need to control not just the particle but every single environmental particle it interacted with, bringing them all back together in exactly the right way. For any macroscopic system, this is impossibly impractical. This is decoherence. The quantum coherence, the delicate phase relationships that allow superpositions to interfere, hasn't actually been destroyed. It's still there, encoded in the correlations between the system and its environment. But it's been diluted across so many degrees of freedom that it becomes effectively inaccessible. From a practical standpoint, the system behaves as if it has collapsed from a quantum superposition into a classical mixture of definite states. Environmental interaction and the speed of classical emergence. The speed at which decoherence occurs depends dramatically on the size of the quantum system and how strongly it interacts with its environment. For a single isolated atom in a carefully prepared vacuum, quantum coherence can persist for seconds, even minutes. Modern atomic clocks exploit this, using the quantum states of individual ions kept in electromagnetic traps, isolated from almost all environmental disturbance. These systems can maintain their quantum nature long enough to measure time with extraordinary precision. But increase the size of the system, and decoherence accelerates exponentially. Consider a dust particle, something you might see floating in a sunbeam. It contains perhaps 10 to the power of 18 atoms. Each of those atoms has electrons that can scatter photons. Even in a modest vacuum, photons from thermal radiation are constantly bouncing off the particle. Each scattering event entangles the particle's position with the photon's state, and those photons quickly fly away, carrying information into the environment. Calculations show that for such a dust particle, quantum coherence between different positions separated by even the particle's own diameter would disappear in a time so short we can barely conceive of it, something like 10 to the power of minus 31 seconds. That's a decimal point followed by 30 zeros and then a 1. For any practical purpose, this dust particle is always classical. It never exhibits quantum superposition in its position because decoherence happens faster than any possible measurement or observation. This environmental interaction explains why we don't see macroscopic quantum effects in everyday life. Your chair, your desk, your own body, these are constantly bombarded by photons, air molecules, and thermal vibrations. The decoherence time for a macroscopic object to exist in a superposition of noticeably different positions is inconceivably short. Quantum superpositions on this scale don't survive long enough to be observed because the environment is constantly, relentlessly measuring them. And here's a subtle but profound point. The environment doesn't need consciousness to measure a quantum system. The very act of physical interaction, of becoming entangled, constitutes a measurement in the quantum mechanical sense. Every scattered photon, every bounced molecule, is gathering information about the system's state and carrying it away. This happens whether or not any conscious observer is paying attention. Decoherence is a physical process, not a philosophical one. The measurement problem revisited. For decades, one of the deepest mysteries in quantum mechanics was the measurement problem. When we're not looking at a quantum system, it evolves smoothly and deterministically according to the Schrödinger equation, spreading out into superpositions of many possibilities. But when we measure it, we always get a definite result. The wave function appears to collapse, suddenly and discontinuously, onto one particular outcome. How and why does this happen? The famous thought experiment known as Schrödinger's cat illustrated this puzzle in vivid terms. Imagine a cat in a sealed box with a quantum device, perhaps a radioactive atom that has a 50-50 chance of decaying within an hour. If it decays, it triggers a mechanism that releases poison, killing the cat. If it doesn't decay, the cat lives. According to quantum mechanics, before we open the box, the atom is in a superposition of decayed and not decayed. And if the atom is in a superposition, and the poison mechanism is entangled with the atom state, then the cat itself should be in a superposition of alive and dead. This seems absurd, and it is. We never observe such macroscopic superpositions. But for decades, physicists argued about when and how the wave function collapsed. Does it happen when the atom decays? When the poison is released? When we open the box? Some interpretations suggested that consciousness was required to collapse the wave function. Others proposed that there were special collapse mechanisms we hadn't discovered yet. Decoherence doesn't completely solve the measurement problem, but it dramatically changes how we think about it. Here's what decoherence tells us. We don't need a special collapse mechanism to explain why we see definite outcomes. The cat, the poison mechanism, the atom, all of these are constantly interacting with their environment. Air molecules in the box are bouncing off the cat. Photons are scattering from its fur. Thermal vibrations are propagating through the box's walls. Each of these interactions entangles the cat's state with the environment. The decoherence time for a cat-sized object to maintain quantum coherence between macroscopically different states like alive and dead would be unimaginably short, far shorter than the time it takes for any quantum process in the atom to play out. Long before we open the box, decoherence has selected a preferred basis, the alive or dead basis, because these states interact very differently with the environment. A living cat is warm, moving, breathing. A dead cat is cold and still. These differences create drastically different patterns of environmental interaction, and decoherence suppresses interference between such distinguishable states almost instantaneously. From the perspective of anything outside the box, the cat is effectively in a classical mixture of alive or dead from the moment the quantum process in the atom occurs, not a quantum superposition. The environment has already performed a measurement, even though no conscious observer has looked. When we finally open the box, we're not collapsing a superposition. We're simply learning which classical state the system decohered into. Does this completely solve the measurement problem? Not entirely. Decoherence explains why we don't see superpositions, why interference vanishes, and why particular states become preferred. But it doesn't explain why, in any individual instance, we get one particular outcome rather than another. It tells us probabilities, but not specifics. Different interpretations of quantum mechanics handle this residual question differently. The many worlds interpretation suggests that all outcomes occur, but in different branches of reality that decohere from each other. Copenhagen-style interpretations treat the probabilities as fundamental. But all modern interpretations recognize that decoherence is the mechanism that makes the quantum world appear classical. Scale and temperature effects. The strength of decoherence depends profoundly on two factors: the size of the quantum system and the temperature of its environment. These aren't independent effects. They work together to determine how long quantum behavior can survive. Size matters because larger objects have more ways to interact with their environment. A single atom has electrons that can absorb and emit photons, but the rates are relatively modest. A molecule has more electrons, plus vibrational and rotational modes that can couple to electromagnetic radiation and molecular collisions. A dust particle has an enormous surface area relative to an atom, providing countless interaction points with environmental photons and air molecules. The decoherence rate scales roughly with the square of the number of particles in the system and with the square of the size of the superposition you're trying to maintain. This scaling is devastating for macroscopic quantum effects. It means that decoherence doesn't just get worse gradually as you make things bigger. It gets worse catastrophically fast. Moving from atoms to molecules to microscopic particles to everyday objects, the coherence time plummets from seconds to nanoseconds to femtoseconds to timescales so short that the very concept of time barely applies. Temperature affects decoherence through the environment's activity level. Temperature is fundamentally about the random thermal motion of particles. At room temperature, air molecules are zipping around at hundreds of meters per second, constantly colliding with everything. Even in a vacuum, any object radiates electromagnetic energy according to its temperature and receives radiation from its surroundings. This thermal radiation consists of photons that can scatter off quantum systems, entangling with them and carrying information away. Cooling a system reduces both of these effects. At lower temperatures, there are fewer air molecules moving around, and those that remain move more slowly, reducing collision rates. Thermal radiation also decreases dramatically as temperature drops. This is why nearly every serious quantum experiment happens at extremely low temperatures. Superconducting quantum computers operate at temperatures below 20 millikelvin, colder than interstellar space, specifically to minimize decoherence from thermal effects. But even perfect cooling doesn't eliminate decoherence entirely. Quantum zero-point fluctuations, the irreducible quantum jitter that exists even at absolute zero, still provide a source of environmental noise. And any interaction with measurement apparatus, any coupling to control fields, creates additional decoherence channels. The battle against decoherence is never fully won. It can only be managed, minimized, and worked around. Understanding these scale and temperature effects has profound practical implications. It tells us where to look for quantum behavior in small, cold, isolated systems, and where not to bother looking in large, warm, environmentally coupled systems. It guides the design of quantum technologies, suggesting what kinds of isolation and cooling are necessary. And it explains, with quantitative precision, why the classical world looks classical. The environment is constantly measuring everything macroscopic, and those measurements happen so fast that quantum superpositions never get a chance to develop. Modern quantum technologies and future horizons. After a century of quantum mechanics explaining the behavior of atoms and particles, we're now witnessing what many call the second quantum revolution. Where the first revolution gave us transistors, lasers, and nuclear power by understanding quantum effects, this second revolution actively harnesses quantum phenomena like superposition and entanglement to create entirely new technologies. These aren't just incremental improvements on existing tools. They represent fundamentally different ways of processing information, communicating securely, and measuring the physical world. Quantum computers and their potential. The quantum computer is perhaps the most famous example of this revolution, and also the most widely misunderstood. Popular accounts often make it sound like quantum computers will simply be faster versions of classical computers, solving any problem more quickly. The reality is both more subtle and more interesting. A classical computer processes information using bits, each of which is definitively either 0 or 1. A quantum computer uses qubits, which can exist in superpositions of 0 and 1 simultaneously. When you have multiple qubits, they don't just represent multiple bits worth of information. They represent all possible combinations of those bits at once, a superposition that grows exponentially with the number of qubits. 3 qubits can be in a superposition representing all 8 possible 3-bit numbers simultaneously. 30 qubits represent over 1 billion combinations at once. This superposition, combined with quantum interference and entanglement between qubits, allows quantum algorithms to explore vast solution spaces in parallel. But here's the crucial limitation. When you measure a quantum computer's output, the superposition collapses. You get only one answer, not all possible answers. The art of quantum algorithm design is finding ways to arrange the interference so that wrong answers cancel out and right answers amplify, making them likely to appear when you perform the final measurement. For some problems, this works spectacularly well. Peter Shor discovered in 1994 that quantum computers could factor large numbers exponentially faster than any known classical algorithm. This has profound implications for cryptography, since most current encryption relies on the difficulty of factoring large numbers. A sufficiently large quantum computer could break these encryption schemes, though we should note that as of early 2026, no quantum computer can yet factor numbers larger than trivial examples. The gap between theory and practice remains substantial. Other quantum algorithms show promise for simulating quantum systems themselves, searching unsorted databases, solving certain optimization problems, and performing specialized types of machine learning. But quantum computers won't replace classical computers for most tasks. They won't browse the web faster or render graphics better or process Word documents more efficiently. They're specialized tools for specific types of problems where quantum mechanical effects provide genuine advantages. As of 2025, the quantum computing field reached several critical milestones. Companies like IBM, Google, IonQ, and others have built quantum processors with hundreds of qubits. Google's Willow chip, featuring 105 superconducting qubits, demonstrated a crucial achievement. As they added more qubits and improved their error correction, the error rate decreased rather than increased. This below-threshold behavior is essential for building larger, fault-tolerant quantum computers. The quantum computing market reached between $1.8 and $3.5 billion in 2025, with projections suggesting growth to over $20 billion by 2030. Major corporations, JP Morgan Chase committed $10 billion in investments naming quantum as strategic technology, and governments worldwide invested over $3 billion in 2024 alone. This isn't hype-driven speculation anymore. Real applications are emerging. In March 2025, IonQ and ONSYS ran a medical device simulation on a 36-qubit quantum computer that outperformed classical high-performance computing by 12%. This represents one of the first documented cases of practical quantum advantage in a real-world application. Similar progress is happening in chemistry and materials science, where quantum simulation could accelerate drug discovery and materials design by allowing researchers to model molecular interactions that are intractable for classical computers. The challenges remain formidable. Qubits are extraordinarily fragile, susceptible to the very decoherence we explored in the first part of this script. Current quantum processors require cooling to temperatures approaching absolute zero, isolation from electromagnetic interference, and constant error correction. Error rates, while improving, are still far higher than classical computer error rates. Scaling from hundreds to millions of qubits while maintaining coherence and connectivity is an enormous engineering challenge. But the trajectory is clear. Error correction techniques are improving, with recent breakthroughs reducing quantum error correction overhead by up to 100 times. Coherence times have increased from microseconds to milliseconds for the best superconducting qubits. IBM plans to introduce a quantum system with 200 logical qubits capable of running 100 million quantum gates by 2029, and aims for 2,000 logical qubits running 1 billion gates by 2033. Different technological approaches are all being pursued simultaneously. Superconducting qubits used by Google and IBM excel at gate operations. Trapped ion qubits, championed by IonQ and others, have naturally long coherence times and high gate fidelity. Neutral atom arrays offer scalability advantages. Photonic quantum computers operate at room temperature, avoiding the massive cooling infrastructure other platforms require. Topological qubits promise inherent error resistance through exotic quantum states. The field hasn't yet converged on a single winner, and diversity of approaches increases the chances that at least one path will lead to practical, scalable quantum computing. Quantum cryptography and security. While quantum computers represent a potential threat to current encryption methods, quantum mechanics also offers solutions for secure communication that are theoretically unbreakable. This is the domain of quantum cryptography, and particularly quantum key distribution. Here's the fundamental idea. If you want to send an encrypted message, you need to share a secret key with the recipient, a string of random numbers known only to the two of you. The security of the message depends entirely on keeping this key secret. Classical key distribution has a fundamental vulnerability. If someone intercepts your key during transmission, and they're clever enough about it, you might never know. They could make a perfect copy and forward the original, leaving no trace. Quantum key distribution exploits a basic principle of quantum mechanics. You cannot measure a quantum system without disturbing it. More precisely, you cannot copy an unknown quantum state perfectly. This is called the no-cloning theorem. If someone tries to intercept and measure quantum states being used to transmit a cryptographic key, they will inevitably introduce detectable errors. Here's how it works in practice. Alice wants to share a secret key with Bob. She prepares individual photons in specific quantum states, encoding bits of the key in properties like polarization. She sends these photons to Bob through an optical fiber. Bob measures each photon, recovering the bit values. They then compare a random subset of their results over a public channel. If an eavesdropper named Eve tried to intercept the photons, her measurements would have disturbed some of them, creating discrepancies between Alice and Bob's subset comparison. If the error rate is too high, they know someone is listening and they discard that key. If the error rate is low enough, they know the transmission was secure, and they use the remaining bits as their shared secret key. This security is guaranteed by the laws of physics, not by mathematical complexity. No amount of computing power can break quantum key distribution without being detected. Even a working quantum computer wouldn't help an eavesdropper. This makes it fundamentally different from classical encryption, which relies on problems being computationally difficult but not impossible. Quantum key distribution is already being deployed in real-world applications. Swiss private banks use it to protect sensitive financial data. Samsung integrated QKD technology into the Galaxy Quantum 2 smartphone through a partnership with SK Telecom. In the United States, Verizon successfully trialed quantum key distribution in Washington, D.C. Hyundai Heavy Industries, the world's largest shipbuilder, implemented quantum cryptography to secure defense technology shipments. The main limitation is distance. Photons get absorbed in optical fibers, limiting transmission range to roughly 100 to 120 kilometers for current systems. Quantum repeaters, devices that can extend entanglement across longer distances without measuring and copying the quantum states, are under development. Satellite-based quantum key distribution offers another solution, using the near vacuum of space to transmit quantum states over much longer distances. Looking forward, quantum communication networks could eventually form a quantum internet, linking quantum computers and quantum sensors in a global infrastructure. Such a network would enable not just ultra-secure communication but also distributed quantum computing, where multiple quantum processors work together on problems too large for any single machine. The integration of quantum cryptography with post-quantum cryptography, new mathematical encryption schemes designed to resist quantum computer attacks, will likely define secure communication in the coming decades. Organizations are already racing to become quantum safe, updating their cryptographic infrastructure before powerful quantum computers emerge. This so-called harvest now, decrypt later threat, where adversaries capture encrypted data today to decrypt with future quantum computers, motivates immediate action even though large-scale quantum computers remain years away. Quantum sensors and metrology. Perhaps the nearest term practical impact of quantum technology comes from quantum sensors. These devices exploit quantum phenomena to measure physical quantities with extraordinary precision. Unlike quantum computers, which require hundreds or thousands of qubits working together, quantum sensors can provide useful capabilities with just a few quantum particles, and they're already being deployed in applications from medical imaging to geological surveying. The fundamental advantage of quantum sensors comes from their exquisite sensitivity to environmental disturbances. Remember that decoherence is caused by environmental interactions disturbing quantum states. For quantum computing, this is a bug, something to suppress and avoid. For quantum sensing, it's a feature. By carefully controlling a quantum system and measuring how it decoheres or how its quantum state changes, you can detect incredibly subtle environmental effects. Atomic clocks represent perhaps the most mature quantum sensing technology. These devices use the precisely defined energy transitions in atoms as a frequency reference, measuring time with extraordinary accuracy. The best optical atomic clocks can measure time so precisely that they would neither gain nor lose more than a second over the entire age of the universe. They're sensitive enough to detect relativistic time dilation from height differences of centimeters. Such precision enables global positioning systems, telecommunications networks, and fundamental physics tests that probe the constants of nature. Quantum magnetometers exploit the magnetic sensitivity of quantum systems to detect tiny magnetic fields. Superconducting quantum interference devices, SQUIDs, can measure magnetic field changes billions of times smaller than Earth's magnetic field. These find applications in brain imaging through magnetoencephalography, geological prospecting for minerals and oil, archaeological exploration to detect buried structures, and materials science research. In 2024, researchers demonstrated the first quantum brain scanner using magnetic field imaging, potentially offering a novel approach to whole brain scanning. Other teams developed quantum magnetometers for navigation in GPS-denied environments, allowing vehicles to determine position without satellite signals by measuring variations in Earth's magnetic field with quantum precision. Quantum gravimeters measure gravitational fields, detecting subtle variations that reveal underground structures or resource deposits. In a remarkable demonstration, researchers installed an absolute atom interferometry gravimeter near Mount Etna, where it continuously monitored gravity changes despite challenging volcanic tremors and harsh environmental conditions. Such quantum gravity sensors could revolutionize geological surveying, infrastructure monitoring, and even fundamental physics research. Atom interferometers, which split and recombine atomic wave packets to create quantum interference, can measure acceleration, rotation, and gravitational gradients with exceptional precision. These have potential applications in navigation, especially for submarines or spacecraft where GPS is unavailable, in detecting gravitational waves from the early universe, and in testing general relativity under extreme conditions. Quantum imaging and sensing can also operate at scales and sensitivities impossible for classical systems. Nanowire array-based quantum sensors achieve single-photon sensitivity, enabling measurements at the atomic scale for biological and materials science research. Quantum-enhanced MRI machines provide higher-resolution medical imaging. Quantum radar systems can detect low-reflectivity objects at room temperature, potentially improving defense systems and security scanners. The Defense Advanced Research Projects Agency launched research programs in optical quantum sensors for military applications, including submarine detection, underground structure identification, and nuclear material sensing. NASA demonstrated ultra-cold quantum sensors in space, opening possibilities for precision measurements in microgravity and astronomical observations with enhanced sensitivity. What makes quantum sensing particularly exciting is that many of these technologies don't require the extreme cooling and isolation needed for quantum computers. While some sensors work best at low temperatures, others function at room temperature or in field conditions. This accessibility means quantum sensors are likely to see widespread practical deployment years before fault-tolerant quantum computers become available. Future possibilities and ongoing research. As we look toward the horizon of quantum technology, the landscape is simultaneously clear and mysterious. We can identify specific technical milestones and see paths toward achieving them, yet the full transformative potential remains difficult to predict. In quantum computing, the next 5 years will likely see continued progress toward fault-tolerant systems capable of running algorithms with millions of operations. The shift from physical qubits to logical qubits, abstract computational units protected by error correction, represents a crucial transition. Companies and research institutions are racing to improve error rates, increase qubit connectivity, and develop more efficient error correction codes. Hybrid quantum classical computing architectures are emerging as a pragmatic path forward. Rather than waiting for purely quantum systems to surpass classical computers across all tasks, these hybrid systems use quantum processors for specific subproblems where they excel, while classical computers handle the rest. This approach is already being used in quantum chemistry simulations, optimization problems, and machine learning applications. The integration of quantum computing with artificial intelligence represents a particularly interesting frontier. Quantum machine learning algorithms could potentially accelerate the training of certain types of neural networks or enable AI systems to solve problems in quantum chemistry and materials science. Conversely, classical AI techniques are being used to optimize quantum algorithms, design better error correction codes, and even help discover new quantum experiments. In quantum communication, satellite networks and quantum repeaters are extending the reach of quantum key distribution toward global scales. China has already demonstrated intercontinental quantum communication using satellites. The European Union, United States, and other nations are investing heavily in quantum communication infrastructure. By the early 2030s, we might see the first truly global quantum-secured communication networks. Quantum sensing continues to expand into new domains. Researchers are exploring quantum sensors for detecting dark matter, measuring variations in fundamental constants of nature, improving medical diagnostics through more sensitive imaging, and enabling navigation systems that don't rely on GPS satellites. The sensitivity of quantum systems to their environment, once seen purely as a challenge, is increasingly recognized as an opportunity. One particularly intriguing area is the intersection of quantum technology with other emerging fields. Quantum-enhanced artificial intelligence could revolutionize drug discovery by simulating molecular interactions at unprecedented accuracy. Quantum sensors might enable new approaches to climate monitoring, detecting subtle changes in gravitational fields that indicate ice sheet movement or ocean current patterns. Quantum communication could provide the secure infrastructure for autonomous vehicle networks or industrial control systems. The talent challenge remains significant. The field needs an estimated 250,000 new quantum professionals globally by 2030. Universities are expanding quantum curricula, companies are training existing employees, and governments are investing in quantum education initiatives. The United Nations designated 2025 as the International Year of Quantum Science and Technology, helping to raise awareness and inspire the next generation of quantum scientists and engineers. Fundamental questions persist. Despite progress on decoherence and error correction, building truly scalable quantum computers requires solving manufacturing challenges that push the limits of current technology. Quantum sensors need to become more robust and portable for widespread deployment. Quantum networks require development of quantum memory and repeater technologies that don't yet exist in practical form. And then there are the unknowns, the applications we can't yet imagine. When John von Neumann wrote about the potential of electronic computers in 1945, he couldn't foresee the internet, smartphones, social media, or artificial intelligence. The digital revolution exceeded the wildest predictions of its pioneers. Quantum technology likely holds similar surprises. We stand at a remarkable moment in technological history. The same quantum mechanics that baffled and amazed scientists a century ago is now being engineered into practical devices. The decoherence that explains why our everyday world appears classical is being carefully managed to preserve quantum effects long enough for computation, communication, and sensing. These aren't mere laboratory curiosities anymore. Quantum technologies are being commercialized, deployed in real applications, and beginning to demonstrate genuine advantages over classical approaches. Investment is surging from both private companies and governments worldwide. Major corporations are committing billions of dollars. National security agencies recognize quantum communication and sensing as strategically important. Yet, for all this progress, quantum technology remains in its infancy. Current quantum computers, impressive as they are, represent perhaps where classical computers were in the 1950s, room-sized machines with limited capabilities but enormous potential. The coming decades will determine whether that potential is realized. The implications extend beyond technology into fundamental understanding. Working with quantum systems forces us to confront the deepest mysteries of nature, the measurement problem, the role of information in physics, the nature of reality itself. As we build quantum technologies, we're not just creating new tools. We're learning to think in fundamentally quantum ways, developing intuitions for a realm that defies common sense. Decoherence teaches us that the quantum and classical worlds aren't separate realms but different perspectives on the same reality. The environment constantly measures quantum systems, selecting particular states and suppressing interference between them. This process bridges quantum and classical, explaining the emergence of the everyday world from quantum substrates. Understanding it has transformed how we interpret quantum mechanics and guides our efforts to protect quantum information from unwanted environmental coupling. The quantum technologies emerging today, computers that harness superposition and entanglement, communication systems secured by the laws of physics, sensors that detect the faintest signals with quantum precision, these represent humanity's growing ability to work with nature at its most fundamental level. We're learning to speak the universe's native language, manipulating quantum states with increasing sophistication and purpose. Where this journey leads remains wonderfully uncertain. Perhaps quantum computers will revolutionize drug discovery and materials science, accelerating solutions to climate change and disease. Perhaps quantum sensors will reveal hidden underground resources or detect the gravitational whispers of the early universe. Perhaps quantum communication networks will provide unbreakable security for an increasingly connected world. Or perhaps the most important applications haven't been imagined yet, waiting to be discovered by researchers who look at quantum phenomena in just the right way. What we can say with confidence is that quantum technology is no longer a distant dream. It's here, emerging from laboratories into the real world, beginning to fulfill the promises and possibilities that physicists glimpsed a century ago when they first encountered the strange rules governing the atomic realm. The second quantum revolution is underway, and its full impact on technology, science, and society remains to be written. If you found this exploration of quantum decoherence and modern quantum technologies fascinating, please consider liking this video and subscribing to Deep Science Sleep for more journeys through the frontiers of science. Until next time, may your quantum states remain coherent, and your dreams be filled with the wonder of the universe at its most fundamental level.